Hi, in this video I will explain how I ran the analysis experiments for the project and how the same experiments can be reproduced from record.txt. I will first show the structure of the record.txt file and the commands used for running the experiments. Then I will discuss the three result tables. I am starting from the project root folder in VS Code here. I have two important files open, config.json and record.txt. And the purpose of record.txt is to make the experiments easy to run again. Instead of adding extra scripts or many extra config files, I kept the workflow simple. For every experiment, we can simply edit the config.json file and then generate input using our workload generator and archive functions, and then read the stats output txt. Here I briefly explain the general run form and how the commands change in various operating systems. I used this command for instance, and this remove item command to remove the clean the database first, and then this get content command to get the stats output. And I believe these are the replacements for them in case you use macOS or Linux, and Python 3 or Python instead of Py can be used in macOS. So the reason I cleaned the .bin files before every run is that this database engine is persistent. If I do not remove old binary files, the next experiment may reuse an old catalog and old relation files or etc. That would make the comparison unfair, so every experiment starts from a clean state. Here we get the outputs from the stats output.txt. This file contains disk reads, disk writes, buffer hits, misses, evictions, and record index counters. And here I define the common workload parameters. Records, I use 500 records, 50 queries, and seed42 in general. The workload generator creates a relation called workload with 6 fields. The primary key is ID, and for each experiment I wrote the exact config values at first, like in here for A1, experiment A1, and then I briefly explained what to do in the A2 or the following other runs to what to change in config.json here to make the other runs. And basically I wrote every commands that you should run before each run of each experiment. Let me briefly do the A1 run. Here I copy config.json here and remove the empty spaces, save it, then copy paste each line from record.txt to terminal. So this is the where it corresponds to. And this is a sequential least recent use run. This corresponds to the first row of our table. It goes like this for every experiment. Now let me go through the three experiment tables and explain what they show. Let's go to the experiment A table. For this experiment, we compare least recent use and most recent use replacement policies. The index strategy is heap scan and the buffer size is fixed at 16 pages. The table shows that MRU performs much better than LRU. For the sequential workload, you can see the numbers here. Least recent use is much better in both cases. It has lower total in and out and higher hit rate. This is a classic sequential scan behavior. The relation is larger than the buffer pool. With heap scan, each query scans the table from beginning to end, and this effect is known as sequential flooding. When the table is larger than the buffer pool and we scan it repeatedly, least recent use keeps evicting pages that will be needed again soon in the next scan, while most recent used replacement policy avoids part of this problem by evicting the most recently used page, which is usually the page we just finished scanning. One important point is that the sequential and random workloads have the same numbers in this experiment. This may look strange at first, but it is expected. The reason is that we use heap scan. Even if the workload generator creates random equality searches, heap scan still scans the full table for each search. So both sequential and range queries and random equality queries become repeated full table scans at the page access level. And let's move on to the experiment B. Here we compare three index strategies: heap scan, hash index, and B+3. Here's the table. For equality queries, a heap scan is clearly the worst. You can see a total of this much, 16,000 of in and outs, while hash and B+ are much better. This is because each equality query searches through the table. Hash index is much better for equality with this you can see total of 2,000 amount of in and outs approximately. And B+3 is even better in this situation, which is actually not the expected case theoretically, and has an explanation. And the reason hash index does not have the lowest total in and out in this experiment, as expected in theoretically, is that our table measures the full workload, including insertion and index maintenance, and in our implementation, maintaining the hash index creates more reads and writes than the B+3 for this workload. That's why B+3 has the lowest total in and out in the equality searches, and I believe this is because the B+3 buffer manager can cache them effectively, and still hash index is almost as good as B+3, even though our implementation for the B+3 might be better than hash index. And for range queries, difference is also clear. B+3 is the best as expected, and hash index follows it, and heap scan is much worse. Again, this is not exactly what is expected theoretically, because hash index should be almost equal to heap scan. It does not support range searches, but this has an explanation as well. Again, we in our measurements included the loading phase, and during insertions, hash index can check duplicate primary keys through the index, while heap scan has to scan the heap repeatedly. So the hash index reduces insertion cost, even though the range queries still use heap scan. That's why in our experiment, hash index seems better than heap scan. But even so, these experiments clearly show the dominance of B+3 in range queries, as expected. I mean, this makes sense because it can go to the first matching leaf and then continue through linked leaf pages. So let's go to the experiment C. For experiment C, I test buffer pool size sensitivity. The workload is random equality search. The replacement policy is least recent use. And the index strategy is B+3. I change the buffer size from 4 to 64 pages as wanted in the description. And the results show a clear trend. As the buffer pool gets larger, disk in and out goes down and hit rate goes up, as you can see here. From 4 to 64, total in and out reduces dramatically while hit rate increases dramatically. This happens because a larger buffer can keep more data pages and index pages in memory. It also reduces evictions and dirty writebacks. In the 64 page case, there are no evictions at all. When I ran the 4 comments here in the last 64 page version, 64 size version of the C experiment, I saw 0 evictions and 0 dirty writebacks, and that means the active working set fits in the buffer pool during the workload. Not only the query phase, so it includes type creation, record insertion, index maintenance queries, and the final statistics snapshot. That is why disk in and out is not 0 even when the buffer pool is large, but the improvement is very clear. Overall, the experiments show 3 main points. First, replacement policy matters when the working set is larger than the buffer. In this workload, most recent use performs better than least recent use for repeated full scans. Second, indexes reduce the amount of record scanning. Hash index is useful for equality lookup, but it cannot handle range search without fallback. B+3 handles both equality and range queries well. Third, buffer pool size has a strong effect on in and out. Larger buffers reduce misses, evictions, and dirty writebacks, especially when the working set can fit in memory. All commands used for these experiments are written in record.txt, and that was all.